Hello, today I'll be presenting on the face mask effectiveness of viral microorganism retention. My name is Joshua Sills, and I have created this presentation solely by myself, and I'm the only creator of the research document. No other classmates were used to create this material. Alrighty, so for the history and background, throughout history, viral diseases have been a means to balance human population growth. This remained prevalent till about 1910. 1910, human population growth began to grow. This is in part due to face masks being first used in operating rooms in Germany and the United States in the 1920s. This spawned a lot of research in the area of germs. Due to this changed in the 1930s. It was an era of antitoxin vaccine development, which can be noticed in any graph, a huge spike in population growth, except for the omitted World War I and World War II. Surgical masks were used worldwide beginning in the 1960s. Due to the United States and Germany's development on this, it led to worldwide adoption. Alright, some technical background. Since the 1960s, a multitude of sources have confirmed surgical mask effectiveness against exasperating or spitting. This has been fairly consistent that spitting is a very high transmitted way of getting viral diseases and germs. Due to this, I'm not examining that in this presentation or paper. However, I'm only examining the spread of aerosols. And this has been done from the SARS-CoV pandemic. Many of my professors and people I talk to on a daily basis believe that aerosols are another likely transmitter, partly because their diameters can range from 30 to 400 nanometers, while most face masks, and for the purposes of this presentation and paper, I will assume my mask to be a surgical mask that contains a hole as small as 300 nanometers. And from my sources, 300 nanometers has been found to be the smallest hole, so I'm going to consider that to be a uniform hole size for the face mask. And this is of particular interest because SARS-CoV and H1N1, or the 2009 flu virus, have diameters of 80 nanometers and 115 nanometers respectively. Now, the CDC claims that there's retention through three ways: internal impactation, interception, and diffusion. All three of these are going to be inspected mathematically and through their definition throughout this presentation. Okay, so beginning with internal impactation. Internal impactation is a filter property for when a particle contains too much inertia due to size or mass, causing the particle to divert from the airstream. This can be depicted in the bottom right hand corner. The red indicates the particle. It's pretty self-explanatory, but some assumptions that are considered here is the filter thread is a perfect uniform circular shape. Obviously this isn't true. A lot of threads that are used in masks actually exhibit more of a rectangular shape or a square shape. However, for the simplicity and purposes of this research paper and presentation, will be assumed to be circular. The capture efficiency of internal impactation is defined as the amount of particles that are absorbed by the filter thread, and this is equivalent to the Stokes number squared. Stokes number is an interesting concept. It's similar to the Reynolds number in that a Stokes number less than 1 indicates particle flow aligned with the airstream, and a Stokes number greater than 1 indicates an erratic particle flow, with a Stokes number around 1 is kind of a mixture in between. So the Stokes number is defined below. All the variables are described. The length of the collector describes the gap between the filter threads, which as discussed is 300 nanometers, and all the other properties can be looked up. The viscosity, though, it's one note, viscosity is of a solid aerosol. And it's also assumed that viscosity of H1N1 and SARS-CoV is the same. That is an assumption as well. So here's the calculations. SARS-CoV is the smaller virus with a 80 nanometer average diameter, and H1N1 has a 115 average diameter. Now that also is something to note, that SARS-CoV has a average diameter of that, and so does H1N1. Aerosols exhibit a scale. In my research, I was able to discover that COVID had a range from about 70 nanometers to 90 nanometers, and H1N1 have about 105 nanometers to 125. So about a 20 nanometer difference. However, this is very noticeable, as will be discussed later. So the capture efficiency for COVID was discovered to be 43.58%, and for H1N1 64.02. This correlates with my predictions, as H1N1 is a larger and therefore heavier molecule, so more should be captured. And internal impactation is the number one way to stop viruses through a filter. Interception. Interception is when small particles throwing the streamline is close to colliding with the filter material, less than 1/2 the particle's diameter. This results in its attachment. For this calculation, as I just discussed, we will now use the 70 nanometer diameter, since it's the smaller aerosols in the scale for COVID, and we use the 105 nanometer for H1N1, as that's on the smaller end of the spectrum. This is only for the smaller molecules. However, an interesting behavior will be exhibited in the calculations. For this, there's 3 layers of the surgical mask filter, which is why I said the capture efficiency is N1 plus N2 plus N3. All those layers actually vary in radius of the circular fiber cross section. The first initial layer is the thickest. So the capture efficiency formula is displayed below. Now I'm going to move on to the calculations. So through this, the second and third layers, the middle and external layers, are actually the same, had the same radius thread that's used, so I was able to calculate them in one equation. So it turns out that COVID has a 4.28% capture efficiency by this method, and H1N1 has a 6.41. Now this remains interesting because even on a smaller spectrum of aerosols, H1N1 is 105 nanometers versus SARS-CoV containing, I believe, 70 nanometers. And this difference, as we go back to the initial slide on the diagram, half of 105 nanometers diameter is greater than half of 70 nanometers diameter, and this results in more being attached to the filter thread. So that is the reasoning behind the percent, and that is discussed more in the research paper. So diffusion is the last method, and it's when a very small particle undergoes a collision with another particle, and this happens sporadically or randomly, causing the particle to diffuse and attach to the filter thread at a random location. As seen in the diagram, this can have some very interesting effects, and it can even attach to, per se, the back of the filter thread. Estimating this quantity is very difficult. You have to use a series of 6 equations, one with the capture efficiency of diffusion, the hydrodynamic factor, flow, and postulate's number. Postulate's number accounts, or actually, let me move on to the next slide because there's more equations. The Cunningham correction factor, or C, accounts for the drag force of all these tiny particles, which can be used in the diffusion constant as from source 19 up there above, which can be used in postulate's number, which can be used in the efficiency of diffusion with the hydrodynamic factor of flow. So there's a lot of equations interplay into this. However, just looking back on the initial concept of what diffusion is allows us to understand mathematically and numerically what these values mean. So here's our calculations for coronavirus. Begin the order as we've discussed, and the efficiency of diffusion is actually 33.66%. I, for one, did not expect this value to be so high. However, looking back onto it, we can tell that since COVID has smaller range of particles, being 70 nanometers on its smaller scale, it should exhibit a higher percentage than H1N1, which remains true, which is 20.95%. So if you can put all these values back to the initial concept, they can make sense, and it's something that you can use to help check yourself if one was ever to recreate this scenario or use these equations. So to apply the Bernoulli's equation, I began by canceling out the Z1 and Z2 terms, as our 2 points is from directly inside the mass to directly outside the mass. I want to determine the velocity the particle is exiting. So I term out Z1 and Z2, and since most surgical masks aren't a perfect seal, there is a concentrated increased pressure right towards the little middle of it. However, I determined this was so small it really wouldn't have affected too much of the results because they're both exposed to atmospheric pressure, so I cancel out pressure 1 and pressure 2. So I was left with V1 squared equals V2 squared divided by 2. Now, to calculate V2, I included the capture efficiencies, and I subtracted these from 1. From a mathematical standpoint, this just made sense. For SARS-CoV, I was able to determine the exit velocity outside the mass to be 1.703 meters per second, and H1N1 to be 1.9713 meters per second. Now this is very interesting, namely because H1N1 is a larger molecular size. One would assume from the beginning of this presentation that H1N1 would exhibit a smaller velocity due to its molecular size. However, this isn't true. So I would say, more importantly, rather than just molecular size and trying to keep a mask that you're developing for, say, having a smaller grid-like pattern, I would optimize it for these three values described above: diffusion, internal impactation, and interception. Okay, so to go to our anhysis simulation, I actually developed this model from a website called, or not a website, a program called Blender. Working through the limitations of anhysis for a simulation so specific for this was difficult. I had to use Blender as a 3D modeling software to actually create a grid-like pattern as seen in this photo to the right. However, this grid-like pattern, I couldn't have it completely accurate to the actual pattern that a surgical mask in real life would exhibit due to the amount of angles, and the size of the file would exceed that of my computer's computing power. So I created a mathematical expression of just a ratio of the particle size to the mask hole size for real mask, and then I use this to adjust the anhysis particle size in the program, and that 2145.672, that is the measured diameter of the holes in the mask, the smallest point. So it's just a way to reduce file size. And through this, I was able to determine the simulation. And all these are about at 5 seconds. So to account for some of the assumed, some of the assumptions here. So all of these were ran in a wind tunnel of the shape shown enclosed here. So all of these lines here are fixed barriers. Now it's kind of hard to see in this image, but all of these are particles, and you can actually see some of them coming back from already impacting this. This would affect some of our results, namely. However, you can see here some of the particles reach as far here and some here. Now what we're going to see is, you actually see that coronavirus exhibits a higher velocity than H1N1 or the flu. Now this is very interesting because going back to our mathematical analysis, we said that coronavirus had a smaller velocity than the flu. However, one thing we also looked at is the diffusion, and diffusion is not accounted for in HYSIS. So diffusion actually gave, per se, the filter's effectiveness for COVID a leg up, and that's why there's a discrepancy in my data, which is also another indication that you cannot trust a simulation purely based on just purely based on it, you really need to look into, especially something that's such a molecular scale. It can use to guide your research, however, it's not an end-all be-all. And for this, we were actually able to create an SIR model. I use this from my differential calculus class in order to find, per se, the infection rate. I made a series of assumptions. One of those is that if you were exposed to someone without a mask, talking to you within 6 feet, or at 6 feet for 20 seconds, then you will contract the virus. This is obviously not a 100% real world situation, and those numbers are not 100%. However, it's going to offer as a difference per se. So we assumed that without a mask that you had 100% contraction. So I found the integral of the black line, which represents no mask velocity over time, measured in HISIS, and that measured out to be about 51. And so then I looked at mask with COVID, and I found the integral of that, and I computed the fraction, and then so now with a mask, I assumed that you had a 52.55% chance of contracting COVID. And this can be seen in the plots here, which is just a simple SIR model. This is more in depth in my paper. However, the red indicates the infected, the green accounts for the recovered and deceased, and the blue accounts for the susceptible. This model definitely lacks a lot of accuracies, but it's a nice depiction to see how wearing a mask, my mathematical data, relates to flattening that curve that you've been hearing so much on the news. So conclusion remarks. Protecting the molecular size of the holes in a mask are a must, and wearing a mask truly does help flatten the curve. To what degree is up to more detailed scientific research, and there's papers with hundreds of pages directly linked to that. However, this report hopes to inspire research for more virus-specific masks, and I'm specifically targeting COVID, but any virus, as a matter of fact, you can develop a mask specifically for that, and that's what this paper is aimed to illustrate in this presentation. And we just need to optimize those properties for things such as internal impactation, interception, and diffusion.